Happy Friday. How's it going, everybody?
Happy Friday.
Happy Friday. Good to meet you, Josh.
Good to meet you too.
Yeah. So on the Friday show, we have Josh Tobin. For people who don't know who you are, do you want to give a quick intro?
Yeah, sure. Hey, everybody, I'm Josh, co-founder and CEO of a machine learning tooling and infrastructure startup called Gantry. My background's in ML research, actually. I was at OpenAI for a few years working on the intersection of deep learning and robotics. We had like a robot hand that's more or less the size of my hand, same degrees of freedom as a human hand, and we were trying to teach it how to do like complex in-hand manipulation tasks like rotating objects and things like that. So really, really fun research problem. The other thing I was working on while I was in grad school and at OpenAI was I co-created this class called Full Stack Deep Learning, which was sort of aimed at teaching people like, hey, the math and the algorithms behind, training machine learning models. What else does it actually take to make these things work in the real world? Um, and that was kind of like the path that led me down into starting a machine learning tooling company.
That's cool.
And yeah, excited to be here.
Awesome. Yeah, I've caught a few of the lectures for full stack deep learning. I think that, especially at the time, I don't think there was anything like it. Because up to then, there were a lot of courses about machine learning, but nothing about how to actually do it in production and so forth.
Yeah, for sure. And I think it was maybe the first of its kind. Maybe there was one or two before, but yeah, it was. It really came out of an observation that Peter, Sergey, and I had. Really independent observations that we all had. That hey, like we're all pretty classically trained in machine learning and deep learning, and we all had sort of separate experiences of trying to take those lessons and apply them to larger teams, more ambitious projects, and found ourselves sort of banging our heads against the wall with stuff that really felt like it must be reinventing the wheel, right? Like I remember discussions at OpenAI about like how should we write unit tests for deep learning code, right? Which is like that seems like such a basic question that why do we need 10 PhDs to answer it? But it turns out that especially at the time, this is probably 2017, there just wasn't really an established best practice. And so that's kind of why we were inspired to start the class.
That's really cool. How did you go about researching the materials for that class? I can't imagine that was easy at that time, especially because there wasn't a lot of resources.
Yeah. Well, it's the first version was largely just based on our experience. And then we also went out and did around 40 or 50 interviews of folks that were kind of in our extended networks who were, in various places building, real world applications of ML. And we kind of tried to lay out what we thought was maybe a conceptual framework for how to think about this. And there were a bunch of places where we felt like we didn't have a good understanding. And so we went and tested those questions with folks. And it's still, I think it's like a living and breathing body of knowledge to this day. Like every time we teach it, we change the content a lot and we incorporate new stuff that's happened in the field and new things that we personally have learned and also new things that we've learned from other conversations that we've had with other practitioners. And yeah, we're doing another version this summer, so it should be. I'm pretty excited about it. There's kind of a renewed focus on like a subset of machine learning applications, which I would frame as machine learning powered products.
Interesting. Well, what is a machine learning powered product?
Yeah, so I think of a machine learning powered product as there's like this broad world of production machine learning, right? Which is like really everything from doing predictive maintenance on machines to like trying to decide where to build your next McDonald's to like trying to decide how your sales force should spend their time to like GPT-3 powered products and DALL-E powered products and recommender systems. There's just a huge breadth of applications of machine learning that fall under this like broad umbrella of production ML. Machine learning powered products I think of as sort of a subset of that, which is defined by the fact that the machine learning model that you're building is meant to interact with an end user. And so the reason that's important, the reason that distinction is important is because as soon as you have end users in the loop, there's sort of like two things that change. The first is it introduces a new kind of risk, which is that, if my, predictive maintenance model is 90% accurate, then that saves me a certain amount of money. But if my recommender system has a similar performance threshold, but 1% of the recommendations are so awful that it's causing users to churn, then that's still a really bad model. And so the first sort of thing that distinguishes machine learning powered products is that since you have end users in the loop, you really need to care about the tails of your performance, not just your average performance. And then the second thing that makes them really different is that since you have users in the loop, you also have an opportunity to learn from those users. So to collect feedback on how your model is doing from how the user, either implicitly or explicitly, from how the users are interacting with the system. And so I think our sort of thesis, both at Full Stack Deep Learning and also at our company Gantry, is that it's productive to sort of think of machine learning powered products as almost like an independent category of production machine learning.
I'm going to ask you a question to follow up from a show a couple days ago. So we had Laszlo Schragner on, and we asked him about AutoML and large language models both. And his comment was that they're really good for generic machine learning problems, not so good for specialized machine learning problems, where even a large language model might be far too general for what you're trying to achieve. Do you agree with that idea, or what do you think about that?
No, hard to disagree. Yeah.
Okay, interesting.
I think, look, large language models they're not right for every application.
Yeah.
But I think the returns to scale in machine learning have continued to surprise me, and I think will continue to surprise us. And so I think at some point, it doesn't make so much sense to train models from scratch anymore for a lot of use cases, right? Like you want to take advantage of the however many millions or tens of millions of dollars that these larger organizations are spending to inject a bunch of basic knowledge into these models. And then you can always specialize them for your task by fine-tuning them. Now, obviously, there's a lot of drawbacks to using large models. Inference is expensive, training is expensive. Inference can be high latency. So it's not for everything, but I definitely think that it's very useful for a lot of specialized applications.
Interesting. And for this crop of machine learning powered products, I suppose, do you have a preference whether like large language models or large models fit into that scope, or small models, or is it kind of everything in between?
Yeah, the way I would think about it is like, I think when we think about like how to categorize different applications of machine learning, a lot of times the way that I've heard people try to categorize them is based on the industry or based on the type of model that you're using. So large language model applications versus recommender systems applications, or maybe based on the type of data that you're consuming. So NLP applications, image applications. I think really a much more productive way to categorize ML applications is based on the problem that you're trying to solve. And one simple reason for that is because, I think really like when it's possible, the right way to build really great machine learning powered products or ML applications in general, sometimes is to start with something really simple and just get it running in production as quickly as possible. And then, ramp up the complexity over time, right? So that in like a lot of organizations that I talk to, that will look like building the first version of your personalization algorithm, just entirely rules-based, right? Based on simple heuristics. That makes it very easy to deploy. It makes it very easy to maintain. And then it also allows you to start collecting data about how that system interacts. And then if you see lift from using machine learning, then maybe the next step is to train a simple model. And then eventually, once your company grows and you have tons of users that are interacting with your system in a really rich way, they're putting text in and things like that, then maybe you add a large language model to embed some of that text input as essentially one of the features to make the model better at solving the tasks that you're looking to solve.
That's really refreshing to hear. I think that's something Matt and I see is there's almost a fetishization of just trying to jump into the deep end, like, oh, it's trained on like TPUs, and it's like a simple classifier.
Yeah, this is sort of like one of the main tenets of the full stack deep learning class from the beginning. It's like start simple, start actually as simple as possible, and then ramp up complexity only as it's really necessary. And this is actually a lesson I learned for the first time in the research world. but it applies very, very well to the production world as well. In the research world, the lesson was that my mentor at OpenAI, I remember once telling me, like, if you ever have a research idea, your first implementation should be like less than 200 lines of code. Ideally, it should be 100 lines of code. And the reason for that is that every line of code that you write introduces a possibility for bugs. And in machine learning, bugs are so hard to detect, right? It's not like your code is just going to error out and tell you, yeah, this line of code is failing. No, what's going to happen is that your model is just going to train a little bit slower, or it's not going to learn anything at all, or it's going to look like it's training faster, but it's actually learning garbage. And so really debugging these systems when you're, especially like when you're building neural nets from scratch, is really difficult. And so that's why it makes sense to start with a really simple set of primitives that should work well, and then add one thing at a time, so you can kind of have a sense check as to whether this is the thing that is causing the new error that I'm seeing.
It's funny. It seems like part of your experience overlaps quite a bit with ours. I think Joe and I come from more of a, let's call it, traditional data science background, as opposed to an ML, maybe deep learning oriented background. But Joe came up with this notion of the recovering data scientist, and it's because when we ran into this problem where we were hired for jobs and actually could not do the job of a data scientist because we didn't have this kind of production support, our response was to go in a different direction.
There was no data upon which to do science.
Yeah.
Let's put it that way too.
Yeah. But yeah, I think what you're talking about really resonates, because a lot of people, from what I've seen, they might learn a lot about deep learning theory, but couldn't even deploy a simple rules-based model. They just have no idea how to even attack a basic problem like that.
Yeah, for sure. I remember doing a consulting project with a company that wanted me to implement reinforcement learning, and they didn't even have a test set. They were training on all of their data. So I was like, I think we have more fundamental things to work on here. But
sure, that's pretty funny. Let's kind of switch to Gantry. It's your new company. What's Gantry up to?
Yeah, so our goal is really to help people, like at the most fundamental level, is to help people build amazing ML-powered products, right? Like I think I'm just a huge believer in this technology, and I think I've only become more optimistic about it over the years as I've been in the field for longer, and things continue to accelerate faster than I was really expecting. And so to me, I think machine learning is on a path to becoming basically part of everything, right? Like, if you go to the grocery store today and you buy bananas, there's like at least 4 or 5 different places in that, in the value chain that led you there, in which you interact with software. And I think, in like 10, 20 years, machine learning is going to be the same way, where it's basically just part of every product or service that we interact with. And so I think this is like huge amount of value that's going to be created. And so at Gantry, we're really focused on helping people build machine learning into their products in a way that's allows them to build great product experiences in a way that's effectively safe. And so what we help with is we basically help you continually improve your models in production. So the challenge with these ML-powered products is that you can never build a perfect model offline without seeing how your users interact with it, because a few things, right? So one is the objective function that you're modeling offline is almost never the one that you really care about in the real world. The second is that real world data tends to change, and so even if you have the perfect objective function offline, that model is not going to be perfect forever. And so as a result, like I think the best machine learning powered products, if you think about like how Tesla is building their self-driving cars, how OpenAI is building its products, they're really, the concept is, I think, similar to what we were talking about before, right? Where you start by deploying something, and then you iterate on that in production. So most machine learning teams don't do this today. Like most machine learning teams, I think a little bit more of their role as like, let's build a model and then throw it over the fence. And, and if something breaks, then like, maybe my PM will like tell me, and then the next day I'll have to go in and like run a bunch of SQL queries and like try to piece together some data and do some ad hoc analyses in a Jupyter notebook. And then like, maybe I'll have like some idea of what went wrong, and I'll like create some charts, and I'll try to convince my team that I have the fix, and then we'll redeploy the model, but you're kind of stuck in the same world. And so what we're really trying to do is like create a structured, systematic, principled way of iterating on models once they've been deployed in production. And so it really starts from being able to detect what's actually going on with your models. So most ML teams really don't have a ton of insight into what happened, like how users are actually interacting with their models once they've been deployed. So that's sort of the first thing that we help with. But I think that's actually not enough. And I think there's been a lot of talk of like sort of ML monitoring, ML observability. I think the issue with that concept is that in traditional software, observability is great, right? Because if I find out that I have a bug in my code somewhere, then I have really good tools to fix that bug, right? I have an IDE, I have unit tests, like all these tools in our toolkit to fix things when they go wrong. In machine learning, it's not really the same, right? Like if you find out that your accuracy is like 2% lower today than it was yesterday, what are you supposed to do about that, right? I mean, it's really not clear. Or if you get a support ticket that says like, hey, your model made one like really bad prediction that a user complained about, like, how do you know if that's really indicative of a broader problem, or if it's something that some way that the user was abusing the system? And in any case, how do you fix it? And so at Gantry, like, we aim to not stop with just detecting problems, but we also are building tools to help diagnose what's going wrong and manage your workflows for fixing those issues. So, helping get the right data labeled, helping create unit tests to make sure that that if you have a certain edge case that is causing a problem for your model, the next version of your model doesn't make the same mistake twice. And so really, if you put this all together, I think of it as sort of like, I think there's a bunch of companies out there that are making the analogy like, oh, we're GitHub for machine learning, right? But I think a lot of times these companies, I feel like, are sort of copying the wrong part of GitHub. Like they're the thing that everyone wants to do is like version control for your data and things like that, right? Which is very important and valuable. But I think the magic of GitHub is not that it's hosted version control, right? Like that's not actually that special. What's magic about GitHub is like the pull request, right? It's these workflow abstractions that sort of define how we work together as a team to build software. And so we're trying to create these types of workflow abstractions that allow people to work together in a really structured, repeatable way on a different task than writing software, which is continuously iterating on machine learning powered products.
Interesting. Matt, you look like you want to say something.
Oh, I was just, I know you mentioned earlier the fact that full stack deep learning, one of the first things you talk about is like, how do you even think about unit tests for machine learning models? So tell us a bit about that, just a short version of it.
Yeah. So I think about unit tests for machine learning models. Let's see how to summarize this in a short version. Basically, the way I think about it is you want to unit test at a bunch of different levels depending on what part of the workflow you're at. So you want to unit test to make sure that you're not having any regressions in your training code itself. And so we advocate for having really simple unit tests that you can run quickly that do things like run a single gradient step of your machine learning algorithm just to make sure that that's working the way that you think it should be working. So that's sort of one category, is like fast tests to make sure that your training process doesn't break. Then there's another category around training, which is like slow tests to make sure your training process doesn't break. So when I was at OpenAI, I remember like we were working on these really complicated reinforcement learning problems, and then we had multiple experiences where like all of a sudden we realized, even though we had made progress on this more complicated RL problem, the simpler RL problem that we had used as a baseline before was broken. Like the training didn't work in our training code. And so, the thing that you want to do to avoid that is also have slower tests that run, every night or every week or something like that, just to make sure that you can reproduce your performance from things that you want to be able to reproduce. So those are tests around training. And there's sort of similar level of thinking around like fast tests and slow tests for inference, like for once you have a trained model, making sure that its behavior doesn't deviate from what you would expect the model to be able to do.
That's interesting. And I guess, is there any sense of interpretability or explainability in these diagnostics as well?
Yeah, it's a good question. I think So the way I think about interpretability and explainability is that explainability is very valuable for certain applications, and in fact, probably necessary for certain applications. But I think that when um, when most people ask for explainability, what they really need is sort of a weaker notion of explainability. So explainability, interpretability, one of those fields of ML where people disagree on definitions. For the sake of argument, let's say explainability means being able to know why the model made a certain prediction that it made. Interpretability means being able to build a mental model for on what types of predictions is the model going to do well and on what types of predictions is the model not going to do well. And then I think there's like sort of a third weaker notion, which is which I don't have a good name for, which is sort of like I think of as understanding the performance envelope of the model. And what I mean by that is, if you think about like in engineering, there are like certain subfields of engineering deal with black box systems all the time, and it's just accepted that we don't actually know why the system works. So the way that you deal with that is through rigorous measurement and testing, right? It's by understanding what performance criteria do we need this component to have, and by creating tests that allow us to make sure that the component operates within those, well within those performance thresholds. And so I think there's sort of a third notion of model of like building confidence in model performance that is more analogous to that. And so I think explainability and interpretability methods as a way of building intuition about what the model is doing, as a way of iterating on what model you should use. If those tools are helpful for you, then that's great, and you should for sure use them. I personally never, as a researcher, never really found them very helpful. But if your goal is to, build confidence that the system does what you think it does, I would advocate for thinking really carefully about what sort of confidence you really need, and then falling back to really careful measurement, because interpretability, explainability methods tend not to be very reliable.
That's very interesting. I like you reframing this in terms of traditional engineering, because I think not enough of that happens. Like people tend to, they treat ML as so exotic. It's like it's this brand new thing that's going to solve civilization, and don't worry about any of that existing engineering knowledge you have. Now, one thing I'll throw into the mix here is that a lot of integration testing in traditional systems is actually very safety focused, because even if you understand all the components, like aircraft testing, right? You know how all the components are supposed to behave, but you still do like these crazy, full speed braking tests and things to see what actually happens when you get into a safety critical situation. Is there a safety aspect to testing of ML models, especially as they're taking over more and more important roles in our lives and in interactions with humans?
Good question.
There is, and I think there should be more of. Yes, like I think if you talk to self-driving car companies about how they think about testing, it's has a similar flavor to what you just described, right? It's like we build a library of scenarios on which we know that we want our vehicle to be able to perform. Some of those scenarios, like sometimes these are sensor data from the vehicle, or we want to know, hey, are we able to perform these really hard detection tasks, or these detection tasks that gave a previous version of my model trouble? Some of these scenarios are simulation scenarios, right? Where it's like, okay, even if we can predict one frame in the future, what's going to happen, is that good enough to actually for the vehicle to be able to navigate these difficult scenarios? And then, some of them actually happen on vehicles. So I think as larger models get used for more and more use cases, I think that school of thinking is going to become more important across ML, right? It's like, and the way I would categorize it is you collect scenarios, and those scenarios are either generated by, your requirements. So in the case of language models, you might want to avoid things like offensive outputs or hateful outputs. So some of those are generated by requirements, and then some are generated as part of the iteration process, where if model N performs really poorly on recognizing children's books, then the way that you might fix that is by curating more data about children's books, or uploading that data in your training set, or potentially adding a rule or a feature that helps the model perform better on that, depending on the use case. But I think you also want to save some of those examples to form a test set, like a mini test set almost, that is part of your like integration testing suite effectively.
That's really cool. Oh, there's a lot to think about. Yeah, I hadn't really thought of the safety aspect before. I think that's actually a really interesting thread that I've never actually heard brought up, in conversations in ML, at least the ones that I have. So I think that's definitely an intelligent way to go. I think especially as you say, ML-powered products are just going to be ubiquitous. And so, and as I kind of look around my room, I see all kinds of products that have safety built into them. Electronic devices, for one, like they should work when you plug them into a wall and not blow up theoretically. So
Yeah. OpenAI had a really interesting blog post. I think it was maybe earlier this week or last week on how they approached this for, I think for DALL-E. So it's worth checking out if folks are interested.
Interesting. What was the synopsis of it?
Yeah, basically like collecting scenarios where the model, that are examples of like the type of behavior that they don't want to allow people to use when they interact with the model. And there's a number of like technical techniques that they use to do that, active learning, these sorts of things.
Yeah, I think there was, what was it? Somebody got pretty pissed off because what was it? Trained DALL-E, or was it GPT-3 on a 8chan or something like that, or something similar? Just
Oh yeah, I saw that on Twitter. It was very controversial. Yeah, it's yeah. I mean, these models can definitely be taught to do things that are terrible, and so it's something to be careful about.
Yep. Yeah, for sure. And it's interesting too, because I think especially as these techniques, get more available to people to try out. I'm both hopeful and very curiously concerned about the path some people take with these very powerful tools. So
Yeah, they are.
Very, very. What are your thoughts on MLOps?
MLOps. Yeah, I mean, I think it's great, right? So I think if you like go back in time 4 years or so to when we started teaching the full stack deep learning class, there were machine learning tools out there. I think we used like a very early version of weights and biases in our first class, for example, but there wasn't really the same ecosystem, and there wasn't really like the same discussion around what are the right practices for building machine learning applications. So I think it's really good. I mean, to me, it's like at a high level, it's a sign that the field is moving in the right direction. I think, and largely, like to some extent, Gantry is an MLOps company, right? So we're definitely also part of this trend. At the same time, though, I feel like MLOps, to some degree, like we've sort of lost the thread. The issue I have right now with MLOps is that I think a lot of what I see in that narrative is really like a kind of like tool fetishization that's not really healthy. I think to me it's like tools are boring, right? Like tools are what you use to do things that are really, really cool. Like to me the exciting part about ML is what you can actually achieve with it, like the products that you can build with it, the automations that you can build with it, the demos that you can build with it. And tools are sort of secondary to that, right? And so I think starting your thinking about ML by thinking about tools like feels very backward to me. And on top of that, right, like the right tool for the job is depends a lot on how you're actually using machine learning. I don't really believe that there's going to be a single canonical ML stack. And the reason for that is that it's the same reason that there's no single canonical software stack, right? It's like there's just such a broad set of use cases for this technology, and building like a text user interface powered by a large language model, or building a like a fraud detection system, or a like a document classifier, or a machine maintenance system. Like these are all really, really different applications. And so I think in many cases, they really need different tools. And in particular, I think, there's a tendency for a lot of folks to just kind of want to copy what they see from other companies. Like, oh, this is how Uber does it, or this is how Airbnb or Facebook does it, and so therefore we should do it that way too. But that's kind of, I think, a logical fallacy, because the reality is, you're not Uber, you're not Airbnb. You have different problems than them, and you operate at a different scale than them. And so I don't think you necessarily need the same set of tools that they do, nor are the tools that they have necessarily correct, right? Like the field has evolved so much in the past 5 years. It's not obvious that, what the state of the art that people came up with in 2017 is really the right thing now. And so, yeah, what I would advocate for is like, which, we're kind of trying to do with full stack deep learning is let's talk more about what we're trying to achieve with ML. And let's talk about how the practices that we use to do that. Let's talk about like, what does it look like for an organization to be great at building ML powered product experiences? What does it mean for a team to be able to like collaborate on creating those experiences in a way that's safe? And and let's put tooling back in the part of the conversation where it belongs, which is like as an enabler of that higher level goal.
Yeah, I think Matt and I see a lot of this too. Kind of call it like cargo hold.
Yes.
Data engineering or data science, where it's just there's just a lot of this, and I think it's the easy path, right? So if you wanted to, where it's theoretically the easy path, because just like, oh, we'll just get some tools and do some stuff, and voila, it's like got Skynet built now. It's cool. Let's do it.
Yeah, exactly. It's like, yes, if we have perfect feature store, then we'll be great at ML. It's like, well, if you're great at ML, you can probably do ML pretty well without a feature store. And I think there's sort of more fundamental things that you need to figure out before that really becomes a piece of technology that you need to adopt. Although it's very, very useful in many use cases. I sort of feel bad saying this because Gantry is also like a ML tooling and infrastructure vendor, so maybe I'm talking against my best interests here. But I really feel like this technology is just so big and so important that like let's make sure we're focusing on the right pieces of it.
I mean, I think one thing the vendors sometimes miss is that they actually gain credibility and might make more sales with more honesty. And so sometimes we act as sort of a go-between for vendors to make recommendations, and sometimes we'll recommend a product that doesn't come from that vendor that brought us in, and let's say, yeah, this doesn't look like a great fit. But then once something does stick, it's way, way more sticky. And so it's definitely refreshing to hear that coming from you, saying it's not just about the tools.
Yeah, I mean, I think, look, like even if it was in my best interest to do otherwise, I wouldn't be able to do it. I think I'm just like too much of a teacher at heart. Like I want to help people like do really cool stuff. And I think our product really helps with that in many use cases, but it's not, I'm never going to come in and say like, it's going to solve all of your problems for you.
Because if you're smart about
product, it's going to solve all your problems. I'm just kidding.
Well, if you're smart about product,
our product is the only one that solves all of your problems.
Yeah, Gantry is the
rest of them are bad tools. Yeah.
Yes. It's kind of funny. I actually just picked this up on accident. My publisher sent me domain-driven design. But what I find interesting about, I mean, this is domain-driven design is an approach in software that's been around for decades, right? But I'm curious to see the I guess the implementation of these practices in the ML space soon, where it's about identifying, okay, so the domain that you're operating in, the business context, all this stuff, right? That's I think up to now has been not as recognized or at least taught, because it's like, well, I mean, you just need to do ML and like that's about it. It doesn't matter what it's for. So,
yeah, I mean, what are like some of the main lessons from that field?
I mean, I only started reading this book about a couple of years ago, but I mean, domain-driven design in general is about the concept of each business is domain, like each practice is a domain, right? And those domains may have services, they may have what's called bounded context against each other, and so, but it's really a separation of concerns, right?
Yeah.
So, I think what I notice often is a lot of the principles of software engineering and the practices inevitably sort of filter down to like data and now into ML and so forth. And so,
yeah, but I think I agree with that, but I think it's really important to apply those principles thoughtfully.
For sure.
Like I would say the principles mostly apply, like the idea of testing in software, the idea of unit testing, integration testing, very applicable to machine learning. Where I take issue with it though is like when people just sort of try to sort of retrofit the exact same not just the principles, but the exact same like set of processes and tools
Right.
into a different domain. And the reality is that like, yes, testing is important, version control is important. All these things are important in ML, but the way that you apply them, I think, is necessarily very different. And I mean, the reason why is that like, well, there's a bunch of reasons, but one example maybe is, I'm not the world's best software engineer, right? But when I sit down to like build a feature for Gantry, not that I really do that much these days, but maybe me 6 months ago or 9 months ago or whatever, like 90% of the time, 95% of the time, I'm able to solve the problem that I was setting out to solve. Call it roughly on the first try, and maybe it's not the best possible way, but it does the thing that it's supposed to do. I've trained a lot of machine learning models, but 90% of the time when I sit down to train a machine learning model, it doesn't work, right? It doesn't do the thing that I wanted it to do. And that's a really profound difference, right? Because it totally changes the way that I think you need to think about your workflow as a developer in that field, right? Like, for example, like the idea, like people sort of wonder why data scientists are so stuck in Jupyter notebooks and things like that. And the reason is because being able to iterate really quickly in machine learning is just more valuable than it is in software engineering. It's very valuable in software engineering too, but in machine learning, it's critical because most of what you do, you're going to throw away. So any extra cost for reproducibility or things like that, it's kind of rational not to want to pay that cost.
That's interesting. And another thing we've noticed specifically, there is this big development of a lot of data observability companies, which totally makes sense, right? So before you even get to model training, observe the data. The easy part of data observability is very similar to what you do in software. And that is check for nulls, check that the data processes are running, check that things show up like adopted ops processes. The hard part is monitoring what I'll call data entropy. And that is you see some massive changes in the data statistics. Is your data corrupt or has the world changed?
Right.
That's a very, very hard question to answer, actually.
Yeah. And I think there's a parallel question in machine learning observability as well, right? Which is like, I think a lot of the narrative around ML observability is sort of has been centered on this question of like measuring data drift. And it's, I don't think it's a very important thing to be able to understand, but I'm not sure it's really the right goal for most ML teams. Like, the idea of like slapping a KL divergence threshold on each of your input features and then you'll know when your model is broken just doesn't make any sense for a bunch of reasons. Like one, KL divergence is probably not the right metric to use. Two, just because one of your features has drifted doesn't mean that your model performance is degraded. Models tend to be robust to some amount of distribution shift. That's why they're models and not just memorizing the training set. And then third, like, what do you actually do about it, right? And so I think what really like the way I tend to think about data drift and things like that is ideally what you should be doing is you should be measuring some sort of outcome when you can, which in ML-powered products as opposed to ML applications where you only get feedback in the far distant future. That's the signal that you want to look at. And then data drift is really useful as a diagnostic tool to help you understand, like, hey, my users are less engaged today. Why? Is it because my model is making worse predictions? And if so, is that because I deployed a bad version of the model? Is it because one of my input features has drifted?
You mentioned goals for ML teams. What are some good goals? If Josh was to design like the coolest ML team on earth, like what would they be focused on, and how would they go about focusing on that?
I don't think I can answer that in the abstract because it just depends so much on your business goals, right? Like, I think ML teams can and should be judged just like every other engineering team in the organization, which sounds like an obvious thing to say, but I actually think that would be not counterintuitive, but that would be like controversial in a lot of machine learning teams. But machine learning teams, exist to serve the needs of the business, and so they should be like building things that help make the company better.
Yeah, there is this weird phenomenon, and maybe you have some thoughts on this too. And I've seen it both at startups and small companies, and that is what will I even call it? It's like the prestige machine learning engineer, right? You're a small startup, you have no budget, but you hire this machine learning engineer so you can say, hey, look at this really experienced person we got from Google. They're going to change the world. And this even happens. I've seen it at big companies where they'll bring in someone. The team may or may not produce anyone, but they just want to be able to point to their ML team for the sake of like juicing the stock value or something like that.
Yeah, for sure. And I think like over the last 10 years, that was really common. I'm seeing it start to change a little bit.
Well, that's good.
Although, like the ML research continues to progress at an extremely fast rate. So I don't think it's going to go anywhere anytime soon, as long as we have, more and more like just really amazing results. But I do think that I have seen a lot of companies that are, have over the past couple of years started to question their investment in machine learning.
Interesting.
Not question it as in like, should we be doing this, but question it as in like, why aren't we getting more value out of this? And I think that we're in the early stages of a shift toward machine learning, like towards companies expecting value out of their machine learning teams that they can measure.
What are some of the factors you're seeing that would cause ML teams or companies not to get as much value as they should out of ML?
I think, so let's take a hypothetical organization, like say, Fortune 500 organization or larger mid-market company. Let's talk through like their journey of adopting ML, right? So journey begins in 2014. They're like someone in their C-suite is taking a business trip. They see a IBM Watson marketing ad in the airport, and they're like, yes, this is the future. This is our strategic priority now. So they come back, and now it's time to like actually start implementing that. So what do they do, right? So they hire some machine learning folks. That's kind of hard. Like, how do you actually get good ML folks? It's still pretty scarce talent. You don't have anything to point to really. And then those ML folks get set up, and there isn't really a clear goal that they're aiming for. And so they spend the next couple of years sort of fighting to get data, trying to figure out like what are the actual tangible problems that we can solve, and trying to create some sort of win, like some sort of justification of their existence. Then fast forward a few years, maybe we're in like 2018, 2019. All of a sudden, you have ML organization has 20 data scientists, and you've produced like a bunch of cool POCs, but none of them have actually gone into production because you haven't invested in infrastructure. But I think maybe more deeply than that, it's because the goal of the team was never really that clear to begin with. And maybe many of the enabling factors weren't really there either, right? Like the data maturity to be able to actually do this stuff. And so I think this is actually one place where tooling will help a lot is, there are some data science teams tend to not to be the best software engineers in the world, like just to be frank. And I mean, I'm sort of, I'm criticizing myself here as well. So it's, I'm allowed to say it. But there is like some degree of software engineering maturity that you need in order to get value out of machine learning. And the way that organizations have really solved this, that have actually gotten a lot of value out of ML so far, is either, hiring unicorns, like hiring folks that are both really good at ML or really good at software, or by building interdisciplinary teams, which is a really hard thing to do as well. Some success also is like from like ML teams sort of tossing models over the fence to some other team that productionizes them, but I don't think that's really as good an approach, and it does require quite a bit more infrastructure.
Is there an approach that can actually work in the real world where you don't unify all the skills on one team, but you can create closer integration between teams? And this is something we've been talking about on the data pipeline side as well, where notoriously application developers will just change upstream data and then break downstream data pipelines, toss it over the fence, except it breaks on the way, kind of thing.
Can you restate the question?
So basically, so you mentioned the approach of like having these cross-disciplinary teams. is it possible to make it work where you have two teams and you somehow make their incentives common enough that they will actually collaborate successfully, or does that not work?
I think it can work. It just requires like a strong culture of ownership and a strong sense of shared goals, which is, practically speaking, is often hard to create. I think maybe like a more robust way of doing it is to define stricter SLAs between the teams. So one thing that I've seen companies start to do that, to your point around like what happens when an upstream team breaks a data pipeline is to define a set of requirements for, okay, so like a common pattern for larger ML organizations is, you have one team that's producing embeddings. So they're taking your product catalog and your user interactions, and they're using a simple model or a large model or whatever to map those into an embedding space that in sort of like a self-supervised way. And then you use those embeddings as one of the features or as the main feature for downstream tasks like recommendations. And so that's kind of an organizational boundary that you can draw, where like one team builds the embedding, the other teams consume the embedding as one of their inputs. And so one thing that I've started to see teams do is like if you have that type of division, you can define SLAs on the embeddings. Like how quickly are those embeddings allowed to change? Who needs to be notified when those embeddings change? What types of end-to-end tests? Like what types of tests does the embeddings team need to pass that take into account the goals of the other teams? So I think I haven't seen a ton of this. I think it's like pretty early days, but I think that approach could be helpful.
Seems cool. You mentioned ML research, and it's your background. What are some of the exciting things you're seeing in ML research right now?
Yeah, ML research is really cool right now. I mean, it's I think, well, I guess like everyone else, like diffusion models, DALL-E, this sort of thing is really exciting. Large language models continue to be really exciting. More and more tasks are sort of falling to the battering ram of scale. And yeah, I mean, I think that's like mostly what I'm tracking right now. I think graph neural nets have a lot of interesting stuff going on. There's a lot of interesting research also in, I would say, like production ML adjacent areas. I'm following that more because that's sort of closer to what I'm interested in these days. But things like how do you, so I talked about the issues like with using drift detection to tell you when to retrain your model, but maybe a metric that is closer to what you really care about is something like approximate model performance. Like given the data that I've seen, given the limited labels that I have, what's my best guess with uncertainty about how I think my model should be performing on those data points? There's been some research in the past couple of years about topics like that I think could be really impactful. Research on active learning, these types of fields that are just going to have, as people build more robust and more and easier to maintain ML systems, are going to have a big impact.
That sounds super cool. And I guess on the flip side, for somebody who wants to learn machine learning, I mean, what would be the things you'd recommend today versus maybe in 2017?
Yeah, I think, for the fundamentals, it's still sort of the same thing, right? I would start with a traditional ML class, like not a deep learning class. I first learned ML from Andrew Ng's class. I think it's still one of the best ways to do it. There's maybe other good resources now that I don't know about. So I think that's a great starting point. And then on the deep learning side, I'm a fan of the fast AI classes. But I think there's a number of really good deep learning classes, like intro to deep learning classes now. And then when it comes time to actually start thinking about, okay, I know a little bit about the models, what do I do with them? Then that's sort of where full stack deep learning comes in.
Interesting. So that progression. And I guess the question I get asked often is how much math do you need to know these days if you want to get into ML?
I'd say very little. Yeah. It depends on how deep you want to go. It's like anything, right? Like if you want to be a software engineer, do you need to understand compilers? No, not really. Do you need to understand operating systems? I don't think so. But would you be a better software engineer if you did understand those things? On the margin, probably, yeah. right? Like understanding how computers work to some degree like affects your ability to build software the right way. I think the same thing is true in machine learning. Like it's never been easier to take an API or take a pre-trained model from Hugging Face and fine tune it on your data and deploy it. It's never been easier to get those types of things to work well. Use AutoML, that kind of thing. But as you get deeper and deeper into the field, and you start to really try to push the limits of performance of what you're trying to do, or you work on more and more complicated problems, then at a certain level, not understanding the math behind it starts to really hurt you, because that's what's under the hood, right? And so it's really helpful to be able to go sort of all the way down to the bottom.
So I come from a pure math background, and what I'll tell you is that the math I've looked at in machine learning courses, the statements of theorems are really, really bad sometimes.
I agree. Yeah.
Okay. So it's not just
I was kind of shocked. Like I was,
Yeah.
I started grad school actually in math PhD program.
Oh, interesting.
And so when I started switching over to machine learning, I was like, but is this really math? I think like part of it is actually just a stylistic thing. But part of it is, like a lot of times the math is, so I think the math that you really need to understand, like for what I'm talking about, is basically just the math of gradient descent, the math of, matrix multiplication, these types of things. Like I think there's a lot of other math in ML papers, convergence proofs, these types of things where, if you really like, where I think even from a practical perspective, there's not a lot of value to knowing. If you want to be a researcher and you want to be able to like make theoretical contributions, then sure. But I think if you understand gradient descent, you understand matrix multiplication, you can read ML papers, understand, the loss functions that people are defining, then I think you're pretty much good there.
I guess my comment about the teaching aspect too was that the problem I have with the proofs I looked at is that they would explain things in terms of matrix multiplication when it would be much better to think of them in terms of properties and linear transformations. Now that probably sounds completely insane for people who don't come from a math background, but I think understanding like the bigger picture of linear algebra and why linear transformations do what they do gives you much deeper insights into machine learning than just being able to multiply matrices together. So it'd be interesting to see if we ever kind of bring it back a bit to more like the core principles of math. So like some of the proofs I looked at, they use all these coordinates. It's like, well, you really only need like one vector and then like a tangent space. And if you understand that, then everything else just falls out really nicely. And it's a better visual picture when you're thinking about machine learning. Anyway, sorry, that's it.
Yeah, that's interesting. Yeah, I feel like it's kind of like there's like a mechanic perspective and an engineer perspective.
Yes.
And I think like a lot of math and machine learning is more like mechanic perspective of like, okay, if you were actually going to sit down and write this as code, like what would it look like? For better and for worse, right? Like I'm all for like building practical understanding of these things. And I think there's a lot of interesting work toward understanding the theory, but I don't think we're quite there yet. So it's not something that I really advocate people spending too much time on unless they're really interested in it.
Yeah, that's a fair point. I mean, and if we think about any mathematical or science discipline, or even something fairly recent like quantum mechanics, I assume it took a long time to kind of dial in like the undergraduate level pedagogy of like, how do you explain the Heisenberg uncertainty principle, for example, where it was really, really hard to get that across at first. Then over time, hopefully we come up with better paradigms for expressing that.
Yeah.
I was going to make a joke about pinpointing something, but I'll refrain. So Hussein has a question here. This is about Gantry. So he wants you to zoom in a bit into the early days when you were doing your user research and coming up with the MVP and prototype. Some questions he has is, how did you validate your product that basically people would buy it? Did you have to do a lot of wireframing and beta release? And I guess finally, how did you convince your investors about the potential growth of your business model?
So a couple thoughts here. We were very lucky in that, from full stack deep learning, we had sort of a community of folks that we could ask questions about what problems they were having and what would be valuable. So sort of an advantage that we had early on. And in many ways, I think the company indirectly came out of that community. On sort of MVP and prototype, like, yeah, I think, my experience has been, it takes a lot of iterations. There's a lot of assumptions that you make when you build a product like this that is something that hasn't really existed before. And so you don't always get it right the first time, or at least we didn't. And so it takes, sometimes multiple tries. And on convincing investor about potential growth, I sort of, I don't know whether this is right or wrong, but I kind of took the opposite approach. Like, I think if you as an investor are not convinced about the potential of machine learning to make a huge impact on the world, then it's not really the kind of investor that I want to work with. But if you do believe that, then I think it's pretty clear that there's opportunities for new, like, better tooling and infrastructure to help make that transition more feasible.
That's a good question. And I guess again, closing out, like, what's it been like going from ML researcher to teacher to CEO and co-founder?
Yeah, it's been really fun. I think each has its own unique set of challenges. I think the fun thing about being a founder is that you get to learn very, very different stuff every day. There's the less fun thing about being a founder is that, I feel like you get like pretty good at a lot of things instead of getting really good at any one thing. And so, maybe the thing I miss most about research is being able to go really, really deep on something. But both are very interesting in their own ways.
Interesting. What were some of the first hires that you made?
We hired engineers first. Yeah.
Okay.
And then we sort of started making the team more interdisciplinary once we had the core engineering folks in place.
That's cool. And I guess maybe what were some of the surprising things you discovered when you started running a business?
Yeah, I guess just how many threads you have to keep going at the same time. And I think one sort of lesson that I have had to relearn many times is you have to kind of simultaneously stay on top of a lot of different things, but also have a really, really clear and singular focus on the one thing that you actually need to get done. Because, I think the traps that you can fall into are one, just sort of losing track of what's going on, which, I think eventually, obviously, as a CEO of a 1,000-person company, you don't know what every single person is working on, but early on, I think is important. And then the other trap would be just being too scattered and not actually really personally making progress on anything. And I've definitely made both of those mistakes at different times. And so it's a difficult thing to do, but is I think pretty important.
Yeah, and it seems like this is the trap that you don't know you're in it until you're in it. Matt and I were just talking about this today with priorities.
Yes.
And it's just you constantly have to make your avoid at all cost list. And this is not your to-do list. This is the 5 things you're going to get done, and all the other 100 things aren't going to get done. That's just how it is. But that list will shift sometimes. But you got to pay attention, because we found ourselves talking about that today, and we're just like, crap, here we are again.
Yep. It happens a lot. And somehow, to do this successfully, you have to strategically decide what to ignore, because you have things that you surface that you think you need to be paying attention to, which might or might not be important. And then you have a lot of other people trying to grab your attention all the time, and their needs might or might not be important, right? So, yeah. And if you ignore the wrong thing, that's bad. If you don't ignore enough, that's also bad.
Completely agree.
Yeah. It's fun times. We're a bunch of maniacs trying to do this.
It seems like.
Well, cool. Josh, it's always fun to talk to you. So
great.
Congrats on Gantry, by the way. Yeah, it's fun for the audience. It's funny too. I was there was a weekend. I was walking around. And I was like, I wonder what happened to Josh Tobin. I haven't heard from him in a while. And then I got an email about Gantry a couple days later. I was like, must be a sign. Let's reconnect.
I was reading your mind. Yeah.
Yeah, he was actually. Yeah, that's what Gantry does. Actually, they just
using machine learning.
Yeah.
Using machine learning, exactly.
Using machine learning. Yeah, because the last time we spoke, you spoke at my meetup. I think it was on the evaluation store, which looks like it sort of
yes.
Right? That was a fantastic talk. People still
Thank you.
talk about that talk all the time, but it was cool. Cool. Well, thanks to the audience. Great questions, great commentary. I'm surprised there's people actually hanging out here on a Friday afternoon before.
Yeah, right before the holiday weekend. I picked a poor date to do this. I realized in retrospect.
Don't worry about it. It's actually good turnout and good response. Yeah, it should be good. We won't be doing the Monday morning data chat because Monday is 4th of July, and that's kind of how that goes. Next Friday, we have a Natty from DBT Labs. He's going to be on talking about all sorts of fun stuff, actually. But in particular, he had a really good blog post on down rounds. And so we're going to talk about money and business because we're just really exciting like that.
It's kind of scary business to discuss right now. So
is what it is.
It is.
And by the way, if you haven't picked up a copy of Fundamentals of Data Engineering, get one. So Matt and I might be able to autograph them for you if you're around or if you send it to us. So, but it's getting some good reviews so far. It's killing it on Amazon
Nice.
in many categories. #1 new release. So
That's awesome. Congrats.
Yeah, thanks, man. Yeah.
Well, we aspire to be the full stack machine learning of data engineering. That's what we went for. If we can get like 50% of the way there, we'll be excited.
I think that's nice, but I think you'll have no trouble getting there. It seems like it also a really interesting field to lay some fundamentals.
Yeah, for sure. Yeah, it's awesome. Cool. Well, have a good weekend, Josh. Good luck with
Bye, everybody.
everything. Yeah, talk to you soon. Bye.
Take care.